Thank you, Sanji, and thank you all for attending this talk. We are going to talk about chemical characterization workflow to improve confidence and identification not only of unknown compounds, but also known compounds. I am Cindy Robertson, and my colleague Joe Buckman is also participating in this discussion. So to give a historical context of how we got to this place in time, ISO 10993 was undergoing significant revisions back in 2017, I believe was when that process started. And we were starting to see what the proposed changes were going to be. Additionally, our vendor-provided software at the time was being discontinued. We had experienced significant issues with the software anytime there was a security update, and so that was very difficult to manage. Our company was also at this time switching from a Windows 7 environment to Windows 10 and Office 365. We started to look for new instrumentation, and our laboratory was starting the process to be ISO 17025 certified. One of those requirements was that the software being used to acquire also needs to be compliant, means traceable, versioning, audit trail, all of those things that are associated with CFR21 Part 11. And I know that that is a specific requirement that's put out by the federal government or the FDA. However, ISO 17025 requires the same requirements as CFR 21 Part 11. We at this time were going to revamp all of our methods. We were going to look into this new software, and also wanted the flexibility of not being stuck with one vendor because we were using vendor-provided software, which brings us to the next slide, which were our business requirements. Our business requirements were that the processing software was required to be instrument agnostic, and that the software had to be capable of being hosted in a virtual environment. We had specified at the time that it had to be Citrix and also able to be hosted in the Horizon View environment. The desire was for this to be a global IT solution where the software could be used in different geographical locations, that we could have the flexibility, because COVID was starting to become a reality, of processing data from home remotely. And we also wanted the so yeah, that was the requirement for the virtual environment. We also wanted it capable of integrating with LIMS and with ELN. We wanted to consolidate spectral data in an enterprise central library/database. That library/database we wanted to be portable, capable of being portable, not necessarily requiring to be in an Oracle database or, fill in the blank database. And the ability to work within the cloud environment or a database environment. And the software, again, just harping on the requirement for traceability and audit trail and versioning and electronic signatures, that would bring us into compliance with CFR 21 Part 11. The data processing requirements. We wanted to have the ability to curate spectral libraries. And the spectral libraries, we didn't want to be limited to curating a flat database. We wanted to curate the database and have plastic additives in one, and things related to different polymers in other databases. So we wanted the flexibility of being able to curate several spectral libraries. We also required an integrated molecular modeling program, molecular formula generator that was compliant with the 7 heuristic rules for molecular formula generator, fragment generator and fragment assignment tools, retention time prediction, and ability to communicate confidence in identification and the quantitation of identified compounds. So just again, to give background, so extractable and leachable work requires that a medical device, or it could be a container or an enclosure for drug products. This also the requirements expand to food containers, where a profile, and also cosmetics, where a profile has to be generated for each of those different containers or the medical device that a toxicologist can take a look at those extraction profiles and predict whether or not do the safety risk assessment to predict whether or not that container, that medical device, is going to cause a risk to the health of the actual individual, the end user. So in that, we have to extract the medical device, we have in different solvents, and then we analyze that through different various techniques. And it is a requirement that all those compounds that are identified have to be, that we have to identify them all, and we need to identify the structure of that compound and be capable of communicating identification, confidence, and the quantitation confidence for those compounds. A huge task. It's not like doing a force degradation study on one particular API. It's where we're actually having to identify everything, and we can have quite a variety from a medical device. So those were our data processing requirements. And back to the instrument agnostic requirement that we have, it was very important that we weren't stuck on a vendor software, that we had to use vendor software for doing those identifications, because if in the future we decide to go from vendor A to vendor B, we want to have that flexibility and not have to make another capital investment in new software. So now I'm going to discuss how known compounds are being identified. So we curate spectral libraries from reference standards and also reference materials. And by reference materials, I'm actually pointing out the actual plastic types that have been compounded with whatever plastic additives they had in there. And we do an exaggerated extraction of those and in different solvents, and we create a spectral library so that the majority of compounds that would need to be identified we are hoping are covered by our reference materials. The reference materials can also be unsterilized, sterilized by different techniques. We do have libraries for all of those. And we are also going to expand those reference materials to be undergoing aging and degradation studies. So what we want, and then by creating these spectral libraries, we are going to search against those spectral libraries. So if we have a device and we know what the plastic types are that are in that, compose that actual device, we can just select the libraries to which that device is comprised. We also have curated spectral libraries for the actual packaging materials. So we've been very deliberate in how we have been going about developing our spectral libraries. So when we're curating records for our spectral library, we take an authentic reference material, and it could be from a certified reference standard. It could be a reference standard that we've used, meaning it's not a certified reference standard, but there is a reference standard out there for it. We will make different concentrations of that reference standard, and we will expose it to our chromatography. And in this case, I'm just showing all of it in our system suitability standard. However, the one that we're going to focus on right here is the N,N-ethylene bisteramide. And when we obtain that, we will actually go through the process of identifying the different fragments, assigning the fragments to the actual structure of the molecule. In Spectra's processor, they have an auto assignment functionality where you can select that molecule has been assigned to a retention time, and now you're going to assign those fragments in both the MS1 spectra and also in the MS2 to the actual molecule itself. And I am showing these slides to show how really well thought out this software is, where it allows for EI, it allows for the soft ionization techniques that we use for LCMS, but this up here is really important if you're going to be using EI on your GCMS. So this tool can be used not just for LCMS data, but it's also can be used for GCMS data. And you can select from this window the different types of reactions that you, or settings that you would want to use. In the next part, there's this spectrum tab, and so you could set your mass range for what your scanning range is. You can say select your relative abundance range, and which is really important when you go to do the matching spectral library searching. And you also have the option of any unassigned peaks you can generate formulas for by clicking on this button right here. And then you could set an AQI threshold. That's the assignment quality index for that particular molecule. And then you have these specific fragmentations that you can select You can use the ones that are common for ESI techniques, and then you can also add the ones that you would want for the GCMS, which is basically blowing the molecule to bits. So in this case, we have done the auto-assign for this particular molecule right here. And you can see up here at the top that we are assigning those, the fragments have been assigned to the molecule. And when you look down here in this MS2 component window, what you see is the red, and that is showing which fragments got matched to this actual molecule. And you can work through this to see how this molecule is actually fragmenting. Once all of the assignment is done, then you would post it to whichever library you would want to. In this case, we would be sending it to our plastic additives database here. But prior to us being able to post that in there, we have to have a review process. So someone will do the assignment, they'll say what it is, someone will go back and review it, and then it gets added into our database. Once it gets added into our database, and this part really goes to being able to express our confidence, but you could see that the fragments that have been assigned to this molecule have been added into the database. And this is for the MS2 spectra, you can actually see down here the different fragment assignments. So those have been assigned to this. We have the ability to add in data. So when we bring this in, we create up here at this root level this entry, and with the molecular structure here. And we're also adding in the retention time for it. We add in the name of the molecule. We assign an external standard to it. And then we have an RRF, the experimentally determined RRF that corresponds to the compound that's being used as the external calibration standard and applying this RRF. And then we also have the ability to assign a CAS reference number to it. And you can see down here, and if you click on these, you can actually see how those have been assigned to this particular molecule. So when you search against that spectral library, you will see we had a match to this N,N-ethylene bisteramide. In the comments, we have put that we know where this is coming from. It's coming from a part of the plastic. And we are able to, and this is actually what an extractable study looked like for this particular device. And in this case, this is the test article. And the assignment, the hit quality for which is the hit quality index, which is this HQI % that's expressed right here, which is evidenced in the component spectrum where you can see the actual mirroring of the reference spectra to the experimental data up here with annotation of the actual different adducts that comprise this spectra. And I forgot to say that when you're actually componentizing this in the IXCR functionality, one can actually define adducts for the actual that you would see consistently. And in this case, we have TEA addicts, but we've also observed a oxidation product of the TEA, which is shown right here. But all of these get grouped together so that one is not forced to do an identification. You don't have a false positive where you're having to identify something that is actually related to the molecule itself. And then we conclude by doing this assignment of the MS2 spectra in this window to the actual molecule shown here. And as you click on each of these fragments in their assignment, you will actually see in red here which part is corresponding to each fragment in this window right here. And now I'm going to turn this over to my colleague.
Thank you. So Cindy has talked about how we identify known compounds using spectral matching and that spectral library that's been curated. And I'm going to talk about how we identify the unknown compounds that are then left over in the sample that need to be identified. And so at a high level, the workflow that we have is to first run a molecular formula generator to determine the molecular formula for the compound, and then use that information and determine a chemical structure that we can confirm with fragment generation and assignment, and then further get confidence in that using retention time prediction. So first, using molecular formula generator, we will generate different molecular formula based on whatever compound we're looking at. And so what you see here is that the molecular formula up at the top, when you highlight it, it shows in the mass spectrum the expected isotopic abundances based on that molecular formula. And what you see in this first example is that there is an ion with M over Z at 185 that is being predicted because it is in red, but it's not actually present in the mass spectrum. So then if we look at our second option here, this one shows good overlap of the predicted isotopic pattern as evident by the red overlapping with the actual pattern seen in the mass spectrum. And so right off the bat, we have more confidence in the molecular formula that we are assuming this unknown is going to be, that we're going to move forward with trying to continue to identify. And so the first thing that we can then do is to start to annotate some of those fragments that we see in the MS2 spectrum. And we do this by using the integrated structure modeling tool to draw the structure that we're proposing to be the structure for this unknown. And we can then use a snipping tool, which is not explicitly shown here, to start to snip apart the bonds, which you can see in how we then identified these different fragments that are matching up with what you see in the MS2 spectrum here. Another tool at our disposal that we use is to look at differences between the various fragments, which you can see here, to look for various patterns that might give us more hints as to what these fragments are. Once we are more confident in the structure that we have, we can run it through the built-in fragmenter tool in ACDLabs software to then see if the fragments that are predicted do match up with what we're seeing in that MS2 spectrum prior to actually assigning it within our data. And so that is what you see here is the output of that built-in fragmenter tool. And once we're confident that what we're seeing is the structure that fits with this unknown. We can then do the assignment in our data by adding in that structure, giving it a name, and then assigning it to the peak that we believe it to be. And this then allows us to, again, run that fragment assignment just like Cindy showed for known compounds, now for this unknown. And what you get is this output up here that shows the various fragments, and it will map them to the MS2 spectrum. And so you can see that all of these fragments are lighting up in red because they're matching with the fragments that were identified. And when you highlight a specific fragment up here, you see this 155. It is then showing you right where that is located on the MS2 spectrum, and in the chemical structure is showing you by mapping those atoms in red that make up that particular fragment, which again allows you to be confident in the assignment that you have proposed for that unknown. And then to further look into that proposed structure, we can also run retention time prediction, which we use the Chrome-Genius function for. And the way that this works is that you first input your compounds and standards that you've run, that you know their retention time, you know their identity, to essentially train the Chrome-Genius functionality. And you also input your method parameters so that the software knows what type of gradient you're running and information like that. So it can then, when you input a proposed structure, predict a retention time within your method for that structure, which pops up over here. And this gives us one more layer of confidence to ensure that the compound that we're proposing is going to elute in approximately the right chromatographic zone as what we're actually seeing in our chromatogram. And so that's what makes this a very powerful tool. And you're able to train this with more and more standards as you run them to even further make this more effective. And so with that, I'm going to turn it back over to Cindy to give our concluding remarks.
Thank you, Joe. And so in conclusion, we selected the software, the ACDLabs database enterprise software, for its ability to be able to curate a spectral library. This significantly improves the efficiency and confidence in our identification and reduces the possibility of false identification due to its ability to componentize all using known adducts and also adducts that have been identified and are unique to your particular method and different solvents. We also have the available tools for unknown identification all in the software, and this aids in expressing our confidence in our proposed identifications. And finally, we are planning some expansions. So the software suite right now is this project started out for LCMS, but we have expanded it to our GCMS data as well. We are also looking into expanding for Percepta, and Percepta is a toxicologist tools for performing their risk assessment on all those compounds that we have identified. The beauty of that is they can pull our data without modifying it into their software, and then they can do their risk assessment within the Percepta software, but using that Oracle data and actually importing it into Percepta. Additionally, there are ability to customize automation, which will make analysis time more efficient. We have already performed the quantitation. We have developed a quantitation script with ACDLabs. So this is a custom, script that we worked with ACDLabs, where when we get done analyzing our data, it will perform that quantitation on our compounds. And so that's already been validated. It selects the correct external standard, and it uses the correct RRF for performing those quantitations. And finally, for the identification of those known compounds, if we have all of that, once the data is produced in our computer or instrument computer, we're working on automating the archival of the data and having pre-processing steps taking place behind the scenes, unknown, without any kind of chemist's intervention, so that when I come in the next day and all I need to do is pull up that data, and I need to review the assignments. I need to and this frees me, and I go through the assignments and I verify the assignments, and it frees up analysts' time for just having to go and spend the long periods of time on those unknown those unknown componentized compounds. This is where our automation will, the custom automation will make this more efficient. And finally, we are also going to be expanding the software to bring in our FTIR data as well. This enables us to generate one unified report for the ENL study that we can provide to toxicologists and to our sponsor, who requires that for an FDA submission. And finally, I thank you for your time and open it up for questions.